Okay, thank you very much for coming today. This is the first DGRAV seminar series. My name is Kent Yagi, and I am an assistant professor at the University of Virginia. It is my pleasure to have this DGRAV seminar series getting started. I would like to thank all the other committee members and also the APS to help me realize this event. So since this is the first seminar series, let me explain in briefly like the scope and format. So we will have this kind of seminar each month, every first Thursday at 3 p.m. Eastern Time. The scope is to help us learn about new subjects and also provide junior researchers with the opportunity to introduce themselves to our community. The format is that we have two speakers each time. The first one is given by a more senior person giving an overview talk for like 15 minutes, followed by a more junior person giving a more detailed research talk for 30 minutes, and then we will have Q&A session at the end. So if you have any questions, feel free to write them on chat, and then I can read out selected questions at the Q&A session, or you can hold on to your questions, and then you can raise your virtual hand and ask questions during the Q&A session. Regarding the name of the seminar series, we did get a few suggestions, but we decided to stick to the original one, which is the DGRAV seminar series. So now this is the official one, but I would like to thank those of you who made the suggestions. And then let's see, so let me move on to introducing today's speaker. So we have two speakers today. The first one is Emmanuel Barty from Johns Hopkins. I think most of you know Emmanuel, and maybe I don't need to introduce him, but let me do that. He received his PhD from University of Rome, La Sapienza in 2002. He did a few postdocs, and then he joined the faculty at the University of Mississippi in 2009, and he moved to Johns Hopkins as full professor in 2018. As you know, he's leading the community in many different ways. For example, he's a fellow of ISGRG. He's a president-elect of ISGRG. He's a fellow of APS. He has served as a chairline of DGRAV, and he's an editorial board member of PRI. The second speaker is Case Wong from Flatiron Institute, and he received his PhD from Johns Hopkins in 2021, last year, under Emmanuel's supervision, and he won Rick Bracchini Thesis Prize in 2021. He has impressive publication record. He has more than 30 publications, which is amazing given the fact that he only graduated last year. I found out from his website that he is an animator and also an athlete. He has some cool videos showing him doing high jumps on his website. So if you're interested, please go and visit his website. He has very interesting hobbies. Okay, I think I talked enough. So let's see. Today's presentation title is Building New Tools for Gravitational Astronomy. So without further ado, I would like Emmanuel to start sharing his screen and then take the floor. Thanks.
Okay. So can you see my presentations full screen?
Yes.
Is it working good? Okay, you hear
Yes.
me fine? Everything is
Yes.
working. Great. Okay. First of all, thank you for the invitation. I don't do high jumps, unlike Case. I would like to keep my presentation as short as possible because it is going to be the main course of this seminar. What I would like to do mostly is to set the stage for his talk. So I will discuss a little bit the background and the motivation for the work that he has been doing during his PhD thesis and the work that he's doing right now at Flatiron. So the general idea here is that I would like to introduce first what is next in gravitational wave astronomy, and in particular, the current plans to develop next generation detectors in the US, in Europe, and in space. And then I will try to explain why the next generation gravitational wave detectors will require the development of new tools and what these new tools are. And I will very briefly explain what kind of new tools Case has been developing and he continued to develop after his graduation, in particular referring to machine learning in the context of population studies and fast parameter estimation for several overlapping sources, which is going to be a major problem as we move forward. So I bet all of you have seen this beautiful diagram by Karanjani and others that shows the first 10 gravitational wave detections. Actually 11, because these are the first 10 binary black holes that were detected and the first binary neutron star that you see in the bottom right. And of course, now we give it all for granted. I still remember the first time I saw GW 150914 and my jaw dropped. You know, we never imagined to see such a loud signal at the very beginning. And then we got used to it, and now we are used to having detections of binary black holes, and the binary neutron star, of course, opened a whole new field of astrophysics with multi-messenger astronomy. But I would say that there were several surprises already in this first catalog of detections. Perhaps the fact that we had seen heavy black holes did not come as a surprise to everyone, but the fact that there seemed to be a gap at high masses in the binary black holes, as you see here, by studying the distribution of the binary black holes, was probably welcomed by several because it seemed to me that what we understood about stellar evolution was correct, and probably there shouldn't be black holes more massive than about 40 or 50 solar masses, and perhaps not so welcome by others who thought the black holes could also form in other ways. And the detections that happened after the first few confirmed that there are many things that, in fact, we do not understand about astrophysical formation of black hole binaries and neutron star binaries and so on. And this is a plot that I like to show very often, where you see that there is a gray population of boring events, if you like, that more or less are similar to the first few that we observed. But then there are lots of other things that we have seen in the following observing runs. In particular, we observed the heaviest neutron star binary that seems to challenge formation scenarios for neutron stars that we had observed up to that point electromagnetically. We started observing neutron star black hole binaries, and perhaps more interestingly, from the point of view of astrophysics, we saw binary black holes with very large mass ratios, mass ratio of order 3. We saw one event in which there is a very puzzling component of 2.6 solar masses that is either the heaviest neutron star we have ever seen or the lightest black hole we have ever observed. And then there was this event, GW 190521, where the component masses fall squarely into the mass gap that seemed to be prohibited if you believed in things like peri-instability supernova or pulsational peri-instability supernova. And so now there's a lot of astro theorists who are scratching their heads trying to explain how you could put an event in the lower mass gap or how you could put events in the upper mass gap and so on. And this is just the beginning. What I want to stress is that we have seen perhaps 90 events, depending on who you talk to, maybe 100. And we already have a lot of surprises. And most of these surprises are coming from the corners of the parameter space, either very large mass ratio events or very massive events, the ones for which we don't have very good waveforms and the ones that we did not expect to be there. And this is only the beginning, because in the United States, recently there was a Horizon study for Cosmic Explorer, which is going to be the next generation gravitational wave observatories here in the US. And in Europe, things are perhaps even more advanced, because the Einstein telescope was included in the 2021 ESFRI roadmap. Don't ask me what that acronym stands for, because I forget every single time, but it basically means that it's on the roadmap to be funded. And now there are things going on like identifying a site for the construction and so on. These detectors will most likely, especially after the pandemic, go online probably in the second half of the 2030s. And by that time, we also expect to have a gravitational wave detector in space, LISA, so that our horizon will expand both in terms of sensitivity on the ground and in terms of having access to a whole new band of gravitational wave observations. And here you see a plot, which has nothing special except for the fact that I made it many years ago, and so I like to show it, where you can see the sensitivity of the O1 and O2 runs, and then the sensitivity of advanced LIGO down here in black. And then you see in red the sensitivity of detectors that have partially already been funded, in particular A+ has been funded, which are better detectors that you can build by using more advanced technology within the existing LIGO facilities. And beyond those, the blue line shows some projected sensitivities for different designs of Cosmic Explorer, and the green lines show projected sensitivities for the expected different designs of the Einstein telescope. Down here, you see the projected sensitivity for different LISA designs. And even though the LISA sensitivity seems to be worse on this diagram, what you have to take into account is that when you go down in mass, you significantly go up in the strength of your signals. And therefore, the typical events that we expect to see in LISA will probably have very high signal to noise ratio if they are, for example, massive black hole binary mergers, just like the events that we expect to see in next generation detectors on the ground. So we are just at the beginning, as I said already, and we have seen perhaps 90 events or so during the runs that we had so far. But astrophysical predictions imply that by the time these detectors go online, we will have something of the order of 10 to the 4 or 10 to the 5 binary black hole and binary neutron star events. And whether there's going to be more binary black holes or binary neutron stars really depends on the astrophysics population theories that you talked. So this progress in sensitivity means that the horizon that we will be able to probe will increase very significantly. So while A+ can only probe out to redshift perhaps 3 or so, with Voyager class detectors, the best detectors that we can build within current LIGO facilities, we will be able to go to redshifts of perhaps 8 or so. That is very important because it means that we will be able to probe the astrophysical population well beyond the redshift of 2 or 3 that corresponds to the peak in the star formation rate. And so perhaps we will see more exotic things like primordial black holes or population 3 stars and so on. But with Cosmic Explorer and the Einstein telescope, we will really be able to observe binary black holes and binary neutron stars throughout the whole universe. And this means that we will see thousands of signals every day. About 10 to the 5 events per year means several thousands of events every day. And hundreds of those binary neutron stars, or perhaps thousands of those binary black holes, will come with a very large signal to noise ratio, larger than about 100. So this means that we're going to have new opportunities, but we also need to develop better data analysis algorithms. And for this purpose, there are ongoing mock data challenges that will try to check whether the tools that we have available now can do the data analysis that we need to do when we have so many events. We will need better computing technologies, and we will need new synergies between the different detectors. The challenges come from different factors. If we have detectors that are more sensitive at low frequencies, it means that the waveforms are going to last in band much longer. If they last in band much longer, it will mean that several of the signals are going to be overlapping. And the high signal to noise ratios mean that we are probably going to be dominated by our imperfect understanding of general relativity rather than by instrumental noise. Also, having so many events is great if you want to do studies of astrophysical populations. They could be a problem if what you're interested in is doing cosmology with stochastic gravitational wave backgrounds, because it will be much harder to detect all of these signals, characterize them, and subtract them to go after the stochastic gravitational wave background. And there's a lot of research going on in these topics. If you are interested, I listed here the archive telephone number for several papers that discuss the rates, parameter estimation in the presence of overlapping sources, the subtraction of the foreground, and the effects of confusion noise on both detection and parameter estimation. The science that we will be able to do with these new detectors is great. I don't have time to discuss it, but if you are interested in all of the different aspects of this, I encourage you to look at the Dawn report, and it's here, sorry, I will skip a slide. The Dawn 6 workshop report, in which the synergy with electromagnetic observations is discussed, and also one of the PAX meetings, one of the many PAX meetings that we have organized recently to discuss the various science aspects of next generation detectors. I want to go back to this slide for a moment because I talked about synergies, and these synergies come in different flavors, but perhaps the most spectacular is the possibility of observing multi-band sources, sources that start in spiraling in the wave band of LISA and then cross over and merge in the LIGO band. And the binary black holes that we have already observed could have been perhaps observed if we had a sensitive enough LISA detector in space already. But there are also intermediate mass black holes that we have not detected so far, and these represent an important discovery space for joint detections by next generation detectors on the ground and detectors in space. The thesis that Case wrote while at Johns Hopkins discusses a little bit all of the different aspects of next generation detectors. He started off by thinking mostly about things like the detection of multi-band binaries and how you could, for example, expand the horizon of LISA by observing events on the ground and then going back to the LISA data to look for events that would have not been detectable otherwise. And he discussed the event rates for multi-band gravitational waves using the astrophysical models. And he did a bunch of papers in which he studied more exotic sources that perhaps may be observable with these next generation detectors, including possibly ultra-short period exoplanets or ultralight bosons and perhaps detection of intermediate mass black holes through the observation of binaries that have a Doppler shift because they are moving around an unseen companion. But then in the second half of his thesis, Case moved more into understanding what kind of algorithms we can develop using new techniques like machine learning for studies of large populations. And at first he did exploratory work where he built deep flow-based generative networks, and then he went on applying these tools to understanding whether we would be able to distinguish neutron star black hole binary populations from double neutron stars, and so on and so forth. So there's a lot of work, as Kent discussed. I don't want to say too much about it, and I want to leave most of the time for Case to discuss what he has been doing even after his PhD thesis. Since when I was introduced to this new DGRAV seminar series, I was told that the idea was to have a mentor-mentee series. I have a few slides with a few thoughts about mentoring. The first is a quote that you have probably heard several times because it comes from one of the towering figures in gravitational physics in the US, John Wheeler. And he famously used to say, we all know that the real reason universities have students is in order to educate the professors. And John Wheeler had some spectacular students. I don't have to tell you who they are because you all know, the John Wheelers and Kip Thornes, and I can, on a much smaller scale, I can say that this is true also in my own personal experience. There's another quote that I wanted to bring up related to mentoring, which is a quote by Edward Gibbon. In case you don't know, as a Roman, Edward Gibbon is the author of Decline and Fall of the Roman Empire. And there's this famous quote that says, the power of instruction is seldom of much efficacy, except in those happy dispositions where it is almost superfluous. So I would like to ask if any of you knows in which context he said this. Is there any taker? I cannot see the chat, so I don't know if anyone is. maybe not. So here's a little thing that you can screenshot and look at it in case you are curious, but it discusses all of this in the context of the decline and fall of the Roman Empire. And he talks about Marcus Aurelius, who was one of the most admired emperors, and how he indulged into feeding the monstrous vices of his son Commodus and casting a shade on the purity of the father's motives, because he sacrificed the happiness of millions of people to a fond partiality for a worthless boy. So, in fact, I only know about this quote because it appears at the beginning of the Feynman lectures on physics. And, you know, if Feynman thought that he was not successful at teaching, then definitely, you know, all of us should think carefully about this. And all I want to say is that, you know, I've been lucky in having very good students, and Case was one of them. And so I will let him talk about what he's been doing and what he's doing now.
Thank you very much, Emanuele, for the great overview talk and also very interesting mentoring slides. Okay, Case, yeah, please start to share the screen and then get started.
Can people hear me and see my screen?
Yes.
Good. Nice. Cool. Like if the people here I don't leave just yet, that's what I'm trying to say. Here is like, you know, somewhat intriguing part that I would say. And I'm gonna talk about, actually, I'm not gonna talk about anything that related to my thesis. I'm the kind of person that, like, once I did certain thing, it becomes so trivial to me that I always don't want to talk about it. But I'm going to talk about something that I'm doing recently, and this should be like an extremely confusing title. It's like, what are you looking at? But as the title of this seminar series said, you know, we're building new tools for gravitational wave. I'm going to introduce a couple tools that I'm working on. And for people who are impatient and want to leave now, I'm going to make a promise. I was testing a promise, and when Emanuele is giving his presentation, we're gonna analyze GW150914 within this presentation. Actually, in the last 10 minutes, we'll have a live demo of that using some of the tools that we built. We're gonna do that. We're gonna complete that, and we're gonna look at the corner plot and have fun with that. So there will be live demo. There will be things that, you know, you can actually go on and try on with yourself. So don't leave just yet if you're wanting to. Okay, cool. Let's hope we get that out of the way. Today I'm gonna talk about, like, here in the bracket is a couple of new tools that, like, recently I've been fixated on, and how we use them for gravitational wave. Now, before I go into the tools, I want to set the stage of what the topics that I'm going to talk about. I'm a fairly junior person, and the way that I feel gravitational wave may not be complete, but I do think in the core of gravitational wave data analysis is the waveform that we have, is the model that we have, because GR is such a nice theory that almost everything is so clean that we have an excellent prediction of how our signal would look like. That, you know, is one critical part of getting the detection, right? Like mass filtering and all that. So in this figure, people should have seen this like many, many times. On the x-axis, you have time. On the y-axis, you have the white and strain. So this is, you know, the deep blue is what a detector will see. If you pose this to a human, they will say, oh, there's nothing there. But apparently there's a very long signal hidden in this data stream. And only because we know the waveform extremely well, we'll be able to match filter it and, you know, basically cross-correlate our model with the data and extract the data out of this really noisy data stream. So at the core of gravitational wave data and data analysis, it's really important to have nice model. Now, for some, like I only realized this yesterday. Oh, this is DGRAV. They must all know gravitational wave. But then maybe that's too much an assumption, right? There may be people that don't look at gravitational wave daily. So let's go over what exactly is a gravitational wave waveform, or what is a gravitational wave waveform model look like? What are the components in it? So on the output side, what you just see is the strain, right? So it's how when a gravitational pass through, how may it stretch your detector and compress your detector and so on. And this is usually represented in either time or frequency domain. In data analysis, we usually represent it in frequency domain just because of a couple perks that brings us in terms of data analysis. And these time series that you see here are parameterized by some parameters that has to do with the source parameters. For example, the masses, the spins, how far it is, the further it's away, the smaller the strain, the heavier this mass, the shorter the signal, stuff like that. So as you change some intrinsic parameters or source parameters, you change how the strain or how the model looks like. And a lot of us usually forget there's some extra parameters in this model. Oh, by the way, like this model on the top right is like something that I steal from GJ's website. He made a video of like, how changing the mass ratio in building the surrogate model that he does will affect the waveform. I was trying to make a point that, changing mass ratio shown by Q does change, the waveform. Let's going back to like one set of parameters that we usually forget are the tuning parameters. So instead of using numerical relativity simulation result directly to analyze our data, which is extremely expensive, you can't really do that in real life, we create approximates of a numerical relativity simulation, very trustworthy models. And in doing that, when we create these approximates or surrogates of the sets of numerical relativity simulation, we introduce some tuning parameters. And these tuning parameters is, you have a pack of grad students coming in, write down a bunch of ansatz, fit some parameters, store them in a table. Then later on, you have a nice and fast function that you can call, and that will generate these waveform. Can people see my cursor, by the way? Just to make sure. Yeah, okay, good. Then you can, call this waveform extremely fast enough that you can do your data analysis. Okay, so that's how gravitational waveform kind of look like on paper. And now I've talked about waveform. Let's think about what are the problems. Well, I mean, I'm just going to tell you nothing about, but like, what are the two problems that kind of bugs me related to, there's an extra square that I forget to animate it. But there are two problems that bugs me it's related to building gravitational waveforms and downstream data analysis. The first thing is I don't really know what really people mean by waveform systematics. I do understand it on paper. On the left here is I think it's the one of the is the heavy event GW19 0521, I believe. And given difference, so on the x and y axis, the two mass inferred given the data. Okay, but people use different waveform approximate. So there's SEO, BNR, Phantom family, and now surrogate. And they use different model, analyze the data, they give different result. And usually people said that's waveform systematic, right? Different waveform models give you different inferred result. Then, there's a systematic, we need to figure that out. But this is, you can have infinite family of like these different model of waveform. Imagine tomorrow I just go wild and make a new waveform model. I can introduce another systematic there, but I don't have a quantitative description of like how this waveform systematic should look like, or how do I the real question that I really care is how do we actually account for waveform systematic when we're doing parameter estimation? The other problem that just grinds me so hard is why parameter estimation takes so long. So if you go on one of the community code that people use to analyze gravitational wave data, Bilby, which is a package that you can pip install and do it. This is a tutorial, this is a screen cap of their tutorial. I'm not dissing them. It's a great tool. It works. It does all the thing. I want to give them credit first, but it takes a while, and it takes a while on a big computer. I think this one runs on 4 cores, takes 15 hours, and this is a signal from a binary black hole, which is relatively short. And as you have a longer and longer signal, like a BNS and so on, they will take longer and longer to analyze, and more and more cores. I was told that in the third LIGO catalog, the total CPU hours spent on analyzing the data is around 100 million hours. I don't know whether that's like entirely accurate or not, but I believe it's somewhere in that ballpark. If you do the math, it's about $1 million USD going into analyzing 80 events. And Emanuele just told us that in the future, we're going to have hundreds of thousands. In the 3G era, it's going to get like millions of events. How much money do we have? Like, we just can't do that. So why does it have to take so long? I mean, it's a sinusoid and it's a time series. You're just matching them. Why should it take hours, and sometime in the binary neutron star case takes weeks? That's unsettling to me. Okay, so that's the two problems that I'm gonna cut. Like the first one, I'm gonna talk about a precursor to how I think we can solve that. The second one is a live demo. I'm gonna show. It is a little bit too bold to say that I'm going to show you the solution. We're going to show you a preliminary pre-alpha version of the solution, which you can download and use. Okay, good. So some tool that we are making, I just want to be clear that this is not just me. I'm working with like people in Hopkins, like Tom Edward, who's a recent postdoc just joined Johns Hopkins under Emanuele's group. Like I have myself, there's a number of contributors, and Max Easy is a postdoc here that we're working very hard together on like parameter estimation. So this is not just my effort, but I have like, students, other postdoc, and, other groups that like we work together. Is really, a team effort. Okay, so some tools. So I talk about the problem, burn that 2 problems in your brain, parameter estimation, huge problem. Okay, now we're just gonna quickly gloss over I'm just gonna show you what are the tools that we are thinking of building or we are building. And I'm going to like just rinse out demo, okay? So first, there's this JAX, the first thing that I want to introduce. We didn't make this, Google made this. It's a Python library that for source code transformation. Again, I forget about the animation, which I don't usually do, but it has several good features. I'm just going to go all of them. What it does is it allows you to write just Python code, like NumPy, very close to what you would learn in like an introductory Python class, and supercharge that. So it has a couple features, like just-in-time compilation. Like compiled code is usually much faster than interpret code, which is Python. And to see what do I mean by compilation here, just-in-time compilation is, you see, you can just write a Python code, like whatever Python syntax that you have here, and you call JIT on it. So this is a function that you write, and you call JIT on it, is pass it into the function, and it just runs 3 times faster. Okay, what it does is actually take your source code, transform it, and not just compile it down to machine code, but it actually compiled it down to accelerator code, like GPU, TPU, like more modern hardware, and optimize for that. And if we want to use GPU and TPU and these hardware that are really good for dense computation, it actually does more than just compiling. It actually, transform your code, then lower it. They figure out some accelerated linear algebra thing. I can go into a total tangent with that, but I'm not going to do that. So compilation is one thing that JAX does. And second thing is automatic differentiation, which I think it's very underappreciated. People start to pick it up, but people usually talk about it in the machine learning context. But basically what it is you can define a function, let's say tangent hyperbolic here. Everyone knows how to take the gradient of tangent hyperbolics. But what it allows is whatever function that you write, let's say you have a generic function f here. You don't need to go into the detail how to do the chain rule by yourself. You can just call grad and tangent hyperbolic. There you go. Now grad 10 is a new function that you can call that will return the gradient down to machine precision. It's not finite differencing. It'll basically transform the code, like, look at the computational graph, transform that into a machine precise level gradient function. Now, this is great. So I'm going to show you how great this is. This is actually, this is the core, one of the few core that motivate the whole machine learning field. And it's extremely important, okay? But just imagine, you go on into writing a 10,000 line of Python code. And you want the gradient now, right? You don't want to go into each term and do the chain rule. What you want to do is just call grad, and then you have a function that gives you the gradient. So that's great. Vectorization, same thing. If I give you a function, you call vmap on it, then this function will automatically batch over, apply like an array. Again, it's not just a for loop. It actually transforms your code and runs things faster. And finally, JAX has support for GPU. That's great. Now, why am I talking about JAX? Why am I talking about this transformation library? So turns out this is the core of what we're gonna like the two library that I'm gonna briefly show you in the next two slides. So the next thing that I want to show is like Ripple, which is a thing that Tom, Edward, Max, and I was working on, mainly Tom. It's a waveform library that we want to write in JAX. So currently we just, we're starting. So we have we support IML Phantom D, where IML Phantom X and more like NL surrogate, these more exotic waveforms are coming. Okay, and the syntax is really loud sweet light. We're trying to mirror loud sweet as much as possible while keeping some of the mirror that JAX has. So you give me a set of source parameters, define your frequency array, jab it in, there you go. There's the IML Phantom D. Not too surprising, not too fascinating, right? This is just IML Phantom D. People have done that already. It's a particular waveform model. What good about that? Now, with Ripple and a decent sized GPU, what we can achieve, like on an 800, we can do 10 to the 7 likelihood evaluation in a second. So this is like, if people have trying to call waveforms before, this should sound absolutely hot wild to you. We basically take the, generates the waveform, this sine curve, integrate it, coarse correlated it, or dot product it against the data 10 to the 7 times in a second, which is about the time of likelihood evaluation that we actually, have inside a PE run. If you take the raw numbers out, we have a PE run in a second, just by likelihood evaluation. I'm not saying that. We have it in a couple minutes, but 10 to the 7. This is something to me. So with JAX, just by writing it in this library, and it allows transfer, compilation, it allows GPU acceleration, a number of stuff. We achieve, just raw computational power. So that's something good. Like this next thing that I have, it's again a JAX-based library, but it's a normalizing flow accelerated MCMC package. That should sound totally gibberish to anyone sitting here. But basically, transformed it in English is a machine learning enhanced sampling package. I don't know whether that helps, but it's a thing that we're going to come back to. But it has a simple interface. It's basically allowed you to do MCMC Markov chain Monte Carlos with some machine learning thing, and but it's just an MCMC package. It has all the properties that an MCMC respects, and it's just faster. It's more generic than just gravitational wave, but it's something that I'm very passionate. We have we can pip install this. I'm going to come back to this. And I'm going to show you the result later. Okay, I think I'm good on time. Okay, so now I'm going to flash two demo, to usage of all this package. So the first thing is, how do we fine tune waveform models? Okay, we have a bunch of new tools, right? How are we going to solve the problems that we have at the beginning? Okay. So the first thing that actually it's a summer student work. It's not so much my work, but I'm going to tell you about something that we kind of did in this space. So as I said before, once you have write down your waveform approximate model, what you need to do is actually tune the parameters to match some sets of numerical relativity simulation. So on the left, I have IML Phantom D, which is kind of a old model that we had. Also the one that we have in Ripple, you need to match that. We basically need to find the tuning parameters in this model that reproduce numerical relativity very well. Now, the thing is, there could be a lot of them. So this table, you don't need to read any of them. The point of this figure is to show you there are over 200 parameters in this model. So there could be a number. And if you only parallelly fit this model by grad student, you need to hire a lot of grad students to fit them. But instead of doing that, we can use, the differentiability of our waveform model. So what we would do is we basically do gradient descent on this 200 dimensional space. And if you ever try without a very accurate gradient descent is a nightmare to do. So in JAX and Ripple, it's actually critical to have the automatic differentiation to get us the correct gradient, then we can do the optimization problem. So this is a preliminary plot that my student has. So what he's actually an undergrad student from Hong Kong. He worked with me over the summer. On the left, we have basically on the x-axis we have frequency, on the y-axis we have like the string of an IMF NMD model compared to a particular NR model, like NR waveform. So in the blue, you show the original IMF NMD model that we taken from the paper. But then we take that model, optimize it a little bit. I mean, he's a summer undergrad student, so by design, he's not gonna have a lot of experience with that. But still, he managed to push down the mismatch from the waveform model to NR by almost a factor of 4, well, more like a factor of 2. Okay, and he repeated this over a huge set of like a couple hundred of numerical relativity simulation, train them, and then deploy them on a set of waveform that you haven't seen before. And you can see like the original in blue here on the x-axis is mismatched. So how well our model match numerical relativity. So that's the x-axis, y-axis is just a histogram. The original is like the unoptimized IMF NMD. The pinkish, reddish color is after we do this optimization, you actually gain a little bit, a tiny little bit, not a lot, but we can push down the mismatch. Like you can actually improve the fit upon, which should not be surprising, right? Like you're fitting something. So, but this is to show with minimal effort, you can actually improve the waveform that you already had, right? Just by simply writing them into a differentiable form and writing them in an automatically differentiable way and optimize it. So that's good. Like you immediately gain accuracy. You kind of pin down waveform systematic by just doing a little bit better optimization. So that's one problem that's pretty promising. I can talk about more like future works in the end. Now, next, parameter estimation. I think I should just go straight to the demo because we have like questions afterward, but just let me briefly give you why parameter estimation is hard. So if we look in a two-dimensional space, so on the left-hand side is the famous GW150914, on the x-axis is the primary mass, on the y-axis is the secondary mass. It's not too complicated to navigate in this space. It's a 2D space. You can grid it and put points in to see whether it's your model is matching the data. But as you go to higher and higher dimensional space, the problem becomes harder and harder. The right is the full posterior for GW150914. And to navigate in this space, you have the curse of dimensionality. So it's kind of harder. I'm not gonna go too deep into like what sampling is. It's just basically comparing your model or your model with your data, basically it. And to really show you what sampling could really mean by at a very low level is imagine comparing pi, computing pi. You don't need to know anything about geometry and all that. All you need to do is draw a circle, draw a random point in this square. Well, if it fall into the circle, you color it with red. And if it fall outside the circle, you color it with blue. And then later on, you count the number of points, like in the two. And magically, you actually get pi out of this experiment. You don't need to know anything about geometry, but you just randomly throw dots and you'll be able to compute some number out of it. This is a demo that I can't, how much more time do I have? I actually don't know.
Yeah, roughly 10 or 8 to 9, but yeah.
Amazing. This is, I'm gonna skip this a little bit. Let's just go to the demo. When I started the demo, then maybe we can look at a couple of things. So this is a live demo session. Now we're gonna look at maybe like during the demo when the code is running, we can come back and talk about a couple of things more about sampling. I'm very passionate about sampling. But people can, I'm gonna actually, let me paste this link in the chat so people can just like go to the GitHub gist to have a look of how does a script look like. But now we're getting into the territory that I'm gonna try running GW150914 in front of you in like whatever remaining time I have. So this is a pretty, I obviously come with a lot of preparation in terms of this, but this is a script that I use to, get the data, clean the data, form your likelihood, then sample. I'm just gonna press run now. I've been running this during before Emanuele, in Emanuele session, so I'm pretty sure. Let me just delete the result. This is one you're just gonna see in a couple of minutes. I'm gonna delete this so I'm not cheating. Oh wait, there's a cut. Delete permanently, okay. that's gone. All right. No, I'm not cheating. Later on, we're going to save an image that gonna reproduce GW150914 in a couple minutes. All right. So the sampler has start is say sampling locally, say sampling globally, training something, a lot of magic's going on. Later, we're gonna come back to that. Now, the code is actually compiling. So I was mentioning Jack's just-in-time compile your code. So the one thing that bugs me is like it's compiling the code now, and usually it takes around 2 minutes. I mean, in this configuration, it takes around 2 minutes or 4. We're still smoothing out the rough edges to try to pin down the compilation time, but it's compiling now. Okay, I just want to come to this and show you guys the code is running. It's compiling now. Now we can kind of get back to the sampling part to talk about what sampling is. So, as I was saying, so in a high dimensional space, sampling it's kind of hard because like the volume to surface ratio is getting bigger and bigger. So let's look at this. This is an interactive gallery that I absolutely love. So let's say you have some target distribution. Let's say I want to sample this banana. We've all seen banana in gravitational wave. What MCMC does is, given the current position that you're standing here, okay, it's trying to propose a new point. So you see it's trying to propose a jump, and it'll reject or accept it according to some criteria. The criteria is proportional to the probability of the target. Okay, so you see like it's rejecting sometime. When the arrow turned red, it's rejecting. When the arrow turned green, it's accepting. So this is basically a bias random walk. It's a bias random walk that it's gonna walk around. Okay, and this proposal now is generated just with a Gaussian. Okay, so you can imagine like if you're just drawing Gaussian around you, and as you go to higher and higher dimension, the Gaussian, like you can see it's not very likely to propose into the region where the target lives, right? If you stand here, you need to propose along the banana, basically. And as you go to higher and higher dimension, you're just going to lose to the volume factors. This is the case when we don't have gradient. Okay, I can tune down the delay, and it will walk around this manifold, and put some sample down, and later you should have the banana. But if we have gradient, we can actually do better than this. That's something called Hamiltonian Monte Carlo. So instead of just randomly drawing Gaussian, we're going to use the gradient information of the manifold and, kind of evolve. You can think of this as rolling a beat down a hill or a valley, and, let it roll a little bit and decide where you want to propose the point. Now you see the trajectory that it draws tends to stay within the target much more. And in this way, it draws like a proposed sample to stay within the target distribution much more. And so that's why your MCMC or Hamiltonian Monte Carlo is going to be more efficient in a higher dimensional space. We can go up to 1,000 dimensional space or even hundreds of thousands. Okay. So, but then Hamiltonian Monte Carlo. So, okay, good. We have a likelihood in JAX. It has gradient. You can do Hamiltonian Monte Carlo. Why do we need case neo magic? Why do we need that? So the reason why we need my stuff, I would argue, is when things become multimodal. You can imagine instead of one valley, you have multiple valley, and because you have gradient, if you don't tune your sampler correctly, let's change the leapfrog step, would be really small. You can actually get trapped in each of the mode. You actually get trapped in that. So we actually need some sort of global understanding of how many valley there are to efficiently jump between mode. And that's what FlowMC kind of does. That's what, oh, my thing is almost finished, my bad. So that's what my sampler does. It uses a machine learning algorithm to try to build a global understanding of the entire manifold and allows jump you propose in between mode. So what I'm showing here is a movie that I think this is an injection run. So it's a simulated data. This is the RA and DEC dimension. which has two very separated modes. If we use like the sampler that we build, which has the gradient component, but also the machine learning component, then you allowed all this jump between the modes. So these different lines that you see here are different walkers, like this chain that just jump between mode, then they can thermalize between mode. Okay, so that's kind of what like my package does. I'm just gonna, put it out there. Okay, so here we are. We have started a run about a couple minutes ago. I think it's 3 or 4 minutes ago. And this package does what exactly I said in like the last minute. It start 1,000 different independent walkers, but as they traverse in these parameters that we care about gravitational wave events, they actually talk to each other through this normalizing flow map, this machine learning map. And again, I think I safely deleted a figure, like, you guys all saw me deleted the figure before, and now here it is. This is GW150914, realistic noise. We fetched it from Guask and all that. I stored it in the binary earlier. But the churn mass is right, eta is, it's there to spin. I checked this beforehand. I checked this to be, consistent with existing parameters. So you can take my word for it. But you can see all these like highly non-local, highly non-trivial features are, all there within a couple minutes. So this is just to show, well, I mean, it's just to show off, to be honest. But we do have the capability with all these tools that we build together, like with our team. We have, like, I don't think parameter estimation should be that long anymore. And as a fact, we showed you parameter estimation can be done in a couple minutes, and you can have the code. Good. So coming to the end, I have introduced a couple tools. Like mainly, I sell JAX and Ripple, like all this differentiable and transformable code library, and also introduced this Flow MC package that I wrote. But remember the two problems that I have, waveform systematic. With differentiable waveform, we are on routes to tackle them. Parameter estimation taking forever. With all these new tools, many likelihood evaluation, machine learning, differentiability, all that combined together, PE in a couple minutes. Okay, so that's the current status. I just want to give people a brief roadmap before we move on to the question. So more waveform models are coming. IML Phantom X, IML Phantom PV2 NR tied for BNS analysis, and NR surrogates are coming probably within this fall. And so people can use it. But we do encourage like waveform modelers to build within this framework, like JAX, open source. If you have problem, let me know, so that we can actually use these great traits that give us real-time PE. And we don't have to do all the lifting. So that's one message. I'm packaging this PE code, as you can go on the code and see it. It's not very clean now. The sampling package is very clean. You can pip install it, use it just fine. But the parameter estimation part, we're going to clean it up. In this month, we should have a ready version to go. You can play around with it. You don't need a black cluster to do hundreds of pre again. Now you can just go on to Google Colab, get their GPU, and run parameter estimation within a minute. Okay, that should be done this year. More detector configuration coming. Currently, we have LIGO, Virgo, all the free detectors. We're putting more detector configuration, 3G, LISA's in. That's gonna take a while because the data analysis problem is different in each detectors, but that's gonna come in a relatively soon term, like in a half a year. Waveform systematic. Once we have more waveform models, we can actually start to explore or even sample. We can sample all these tuning parameters. We can have, instead of doing 15-dimension sampling, we can do 200-dimension sampling. That we can actually totally incorporate the waveform systematic into our posterior and marginalize them. And finally, I just want to add one more mark here is we're also doing some testing GR study. One thing that testing GR always face as a kind of criticism is we always kind of fix one term and fix all the other term and vary them because a high dimensional inference problem is hard. Now we just give you the tool. It's no longer hard. It can be multimodality. It can be highly non-local, highly correlated thing. sampler can probably handle that. Now, like there's all these like flashy development codes and all that. You should be very skeptical, and I encourage people to be skeptical. But the take-home message is, like all these tools are online. Like we want to be very open about it. People should be able to look at it. If you go on my GitHub, you can see all the things that I was talking about: FlowMC, JAX G-Wave, Ripple, they're all there. All I want to say is give new tools a chance, and they can do wonder. Question.
Thank you, Case, for a very unique and live demonstration. Okay, so we only have like 4 minutes, and Emmanuel has to leave at 4, so we'll end on time. But if you have any questions, please raise your virtual hand or type your question on chat. And then Satya, please go first.
Case, this is a fantastic work. Thank you very much for writing all these tools. They are very critical for next generation observatories. I just want to ask you 2 questions. At the moment, I have many more. For binary neutron stars, how long does it take?
5 minutes or 8. Yeah, 8. We're trying a GW1708 one. So one critical bit is like heterodyne likelihood that compress the number of samples. Then you parallelize over GPU. So binary neutron star is actually not much longer. We've done injection with, I think I tried a segment length of around 500 seconds. That takes a little bit longer, about 10 minutes.
Okay, I think it would be nice to have an idea because there are other approaches to this, the so-called relative binning, or you have heard of those things, I'm sure.
Relative binning is exactly the same as heterodyne likelihood, different term, but we're using
heterodyne. Exactly, exactly. It's the same
we're using
thing.
that.
So we are seeing something like 10-15 minutes, and I'm told by the developers they're hopeful that will be 2 to 3 minutes. This is extremely good news. But I want to ask you my second question, which is, are we going to be able to analyze simultaneously some kind of a global analysis with hundreds of signals at the same time? Thank you.
Yeah, I think we need to build a model for that one first. If you don't have like a good likelihood function, it's not going to do that. But in cosmology, like people have tried to infer 10 to the, I think, let me get a number right, 128 cubes. So around 10 to the 6 parameter at the same times. So as long as you stay behind, like it's below that HMC, like with some, I mean, it's engineeringly hard, but it's engineeringly doable. So we should be able to do that.
Okay, thank you.
Yeah.
And good luck with all the development work, great development work you guys are doing.
Thanks.
Theo?
Nice talk, Case. So I've used Numba before, which also does just-in-time compilation. I haven't used JAX. I know some people are doing stuff in Julia, which also does just-in-time compilation.
Right.
So where should we be spending our efforts, right? It seems like lots of people are taking high-level code to, do automatic differentiation, just-in-time compilation, etc.
Yeah.
Where do we spend our time?
I think what a reasonable thing for the community to do is I think it will be very inefficient for 100 people to all trying to learn JAX in the same time, trying to figure out whether JAX will work for their problem. Because Julia, JAX, Numba, they have like different just-in-time compilation scheme, and they fit for different problem. If I tell you JAX is the best in general, Julia is the best in the general, that will be a lie. That will be, it's a little bit problem specific. I would say JAX it's reasonably easy to try. Julia is a completely different language you need to learn again. Numba is easier for integration. I think in terms of trying, Numba and JAX is closer. They're not that different, although I think JAX do have a little bit more performance gain, especially working on an accelerator. So I do think people should take some time to just take a day, learn how to do JAX with a toy problem. Then if it doesn't work for your problem, forget it. But in terms of what people should spend time on, send me an email, spending time sending an email, and, we can talk about whether or other expert in the field that have better understanding of like these new tools, then we can figure out whether the modeling process, will the new tools be suitable for the particular class of problem? Because those usually needs some time to figure out. Yeah. Does that answer the question? I don't know. What about, if you want a short answer, like look at checks for a day, then stop, maybe.
Yeah. So instead of sending you an email, how about I just say, can you make the surrogate code differentiable with
Oh, we're
Jax?
doing that. We're doing
great.
that. Yeah, yeah.
Excellent.
It's gonna come. Yeah.
Thanks.
Cool.
Okay, last question from Thomas and Emmanuel. If you have to leave them, feel free to leave.
Yeah. So I just want first I want to just thank both of you, Case and Emmanuel, for a great talk. So I thought this was a great inaugural talk or presentations for this seminar series. So thank you very much for putting the effort into it. And I have one quick and specific question, or actually two related questions. You talked about this grad functionality of JAX, and what I missed is, does it actually do the differentiation symbolically, or does it do it numerically? And then basically my follow-up question is, which you also compared it with getting these gradients from finite differencing. And I'm wondering which feature is actually crucial for speeding up your searches. Is it that you get the gradient more accurately, or that you can compute it more quickly using this feature?
We can compute it more quickly. Like, let me answer the second question because I like technical question first. So automatic differentiation, you can think of chain rule. It's basically chain rule. So you write down sine 2x, right? But that you can write it in a computational graph. And if you see a sign, you know how to do chain rule on the sign. You just replace it with a whole sign. This, like, the fundamental idea of how automatic differentiation works is, go into the computational graph, transform it into a different computational graph fundamentally, conceptually. I mean, there's tricks that people do. But so it's not finite differencing. It's also not symbolic differentiation, because symbolic differentiation suffer the expression swelling problem that, they grow. And, automatic differentiation can even works on for loops, so like control flow, the span graph. It's generating really, different code. In terms of finite differencing, I think finite differencing suffer from either truncation error or round off error. They have like this, error curve. But automatic differentiation, again, because it's a co-transformation, it doesn't suffer from that. It's, as exact as, machine precision goes. So the fact that, you're doing this transformation of graph, you don't need to evaluate on your stencil. You don't need to call the function twice, or in 3D, you don't need to call your function like 8 times to compute the finite difference. So that usually, there's some exception. I mean, there's a lot of exceptions, but very often the computation time for the gradient is of the order of your function evaluation. So that's actually, very, very helpful because you don't need to call your function multiple times. That was the second question. What's the first question again? Sorry, did I miss that?
Actually, I think you answered both of them already.
Okay, good.
So one was it actually automatic differentiation versus finite differencing? And then is it the speed or the accuracy that actually helps is the key improvement in your searches?
I think it's mostly it's the speed. I mean, like the accuracy is like automatically guaranteed. So it's mostly speed.
Yeah, great. Thank you.
Thank you.
Hey, great. Thank you very much, Emmanuel and Case, for the great presentation again. So next seminar is on November 3rd by Asimina Armenitaki and Masha Variatar. So I hope to see you all in November again. And then thank you very much for coming today. Have a nice evening. I'll see you in November.
Thank you all.
Bye. Bye. Bye.